Swayam Prabha. Digital India. Educated India.
In this module, we will be looking at details of acoustic material. So far we have been talking about basics of acoustics and indoor acoustic treatment. The last module we were talking in elaborate about considerations for acoustical design in buildings, where material selection is a very crucial part. Unless you select a right material, your acoustics is not going to be alright. So this module will primarily focus on types of acoustic material, absorbing materials, insulating materials. Primarily we will be starting with indices for measuring. What parameter should we look at? Say if you have to select from a list from a seller, what parameter you should be keenly looking for, and then what are the types of materials available and their specific applications. A quick recap of what we saw last time. This was a reverberation time equation. This is Sebine's formula, where you have reverberation time which is equal to 0.163 volume by the absorption. A is alpha, that is called absorption coefficient of specific material into the surface area of that particular material's application. So if you have n number of materials spread over specific surface areas, then you can have a sigma, that is specific absorption coefficient which into the surface area. This particular number A is referred in terms of absorption, is referred in terms of Sabin, that is a unit for absorption. Now we will look at more closely about what this alpha actually means. Alpha is the absorption coefficient of a particular material. It ranges from 0 to 1. 1 is 100% absorbing, 0 is 100% reflecting, that is does not have any specific absorption. This particular absorption or alpha absorption coefficient varies with respect to frequency. So ideally when you select a material, if you want a real performance based selection, it is rather better to look at least 3 specific absorption coefficient, that is absorption in the low frequency, something around 63 or 125 hertz or sometime 250 hertz. Better is to look at 63 and 125 hertz. Then in the mid frequency range, that is around 1000 hertz, what is the absorption coefficient, and in the high frequency range something after 4000, say 8000 hertz is a good indicator of high frequency absorption. There are 2 different types of tests through which absorption coefficient itself is determined. First is called reverberant chamber method. We talked about 2 different types of chambers. First was the reverberant chamber, other is an anechoic chamber. We had these references in the last module. Reverberant chamber is a place or a testing room where the acoustic absorption is almost 0. It has infinite reflections or the reverberation time is very large. On the other hand, anechoic chamber is something where there are almost no reflections and the absorption is very high, the reverberation time is very low. This is what makes the difference. So the first method, you place the material to be tested, you mount it inside the reverberant chamber and you test the difference between the original reverberation time and the reverberation time after the material is placed inside the room. Typically test chambers have their own reverberation time without any material present. When the material is present, there is a second T dash or the second reverberation time. With this you can find out what is the reverberation absorption coefficient of this particular material. This method of testing is more efficient for frequencies between 100 to 5000 hertz, and there are a lot of other considerations like mounting, on what surface you are mounting, edge diffraction, lot of other things are coming. We are not looking into those specifications right now. Just for information, this is the first method and the second method is called impedance tube method. We studied about the principle of standing waves. This particular principle is applied in this testing. I will quickly show you the chambers and the testing devices. This is a reverberant chamber. You place the material inside the chamber, it has infinite reflections or the reverberation time is very long. Without any material, the chamber's reverberation time is taken, and after the material is mounted, then the absorption is measured. There are various advancements in this method of measurement. This is an anechoic chamber for your information. It has a lot of wedge shaped, each one is an absorbing surface. So the surface area is very high and the absorption is really high. The reverberation time will be very low, negligible reverberation time. This is a second type of measurement which is called standing wave method or the impedance tube method. This is a typical experimental setup. It is available as a testing device or you can fabricate your own. This diameter of the tube and the length of the tube has a critical position to play in terms of the testing efficiencies. Say this kind of thinner tubes, thin diameter, smaller radius tubes are used for high frequency testing, the larger ones used for typically low frequency testing. On one side of it you mount the material, there is a signal generator or a pure tone generator, specific frequency is set in which tones are produced. A principle of standing waves are formed in inside this chamber. Then you have a microphone which is recording the typical high and low, that is the maxima and minima of the wavelengths, with which a specific calculation procedure will tell you what is the absorption coefficient. So this is the second method of testing. Using these methods, typically you determine at specific frequencies what is the absorption coefficient. This is what we are referring as alpha. So when we say a specific material is there, let us take for example the red line here, this is a material X, or say for a example we can say it is a cushion, it is a 50 mm cushion, you are testing this. So at different frequencies starting from 125 where you are getting about negligible absorption, then you go all the way up to 4000 where you are getting about 0.8 alpha or absorption coefficient. The material is having a good absorption in the high frequency versus it has a very negligible or low absorption in the low frequencies. You take another material Y where you are mounting it, say for example it could be a glass wool behind a particular panel or a fabric. You are testing this particular thing, again say 50 to 75 mm, which has a different type of alpha value. At 125 hertz it has slightly better absorption, 0.4, 0.5, mid frequency is close to 500, it is okay. After mid frequency it has very low absorption. Commonly when you buy a material, you have a value called NRC or noise reduction coefficient, which is nothing but an average absorption coefficient of 4 different frequencies, 250, 500, 1000 and 2000. Any material you choose, the first index or the number you get to see or refer or the supplier gives you will be the noise reduction coefficient. They will say the NRC value is 0.8, 0.9, so it is a good absorbing material. Yes, it indicates the material's absorbing performance, but one short note you have to remember, it is an average value. So take the case of two materials that we were comparing, material X and material Y, both of them the absorbing pattern is different. First material has good absorption in the high frequency, low frequency it is not performing well, whereas the other material, the material Y, has the totally reverse type of performance. In the low frequency range it is better, as it gets higher the absorption is coming down, but as you see the NRC, both have around 0.4 NRC. So in this way NRC as such, simply referring to NRC is little misleading. So it is rather a good idea or a better strategy to look at what is the specific absorption coefficient at different frequencies. If you take a closer look, if you want to control reflections or if you want more absorption in the low frequency, if your reverberation time calculation shows that your RT at the low frequency needs to be reduced, then you need to go for material Y in place of material X. On the other hand, if you find that mid and high frequency you need more absorption, or at specific location you need to arrest mid and high frequency sounds, then better go for material X. So NRC as such is a good indicator for absorption coefficient of a material, but since it is an average, it sometimes is misleading because it averages out both high, mid and all the three, high, mid and low frequencies. Another consideration you have to be careful about while you choose a material. For instance, I have given an example, you are wanting to buy a carpet and the material supplier says the carpet has an NRC of 0.8, which means it is an extremely good absorbing material. So typically you will prefer going for this particular carpet, but if you closely take a look at it, the mounting condition in which the material was tested, was it only the carpet or was there any backing given to the carpet? In this case, for example, if the carpet was installed over a block of fiberglass or a panel of fiberglass, then this NRC, particular NRC of 0.8 actually refers to a better absorption not just of the carpet, but it is carpet as well as the backing or the fiberglass, glass wool backing, which is resulting in this 0.8. It is not the sole performance of the carpet alone. So better you also ask the supplier or check for the database in the data sheets what was the mounting condition. If you take a closer look, then your material selection is more economical or more trustable. There are three types, primary types of acoustic absorbers. First is porous absorbing material, second is panel absorber, and the last is cavity resonators. Each one has a specific bandwidth or frequency spectrum in which they have a very good performance. It can be stretched out to other frequencies, but their primary performance area are different. Take a porous material, any type of cushion, glass wool, you have boards, there are few varieties I will show you now. Simple example is a cushion or a foam, acoustic foam, which will have very good absorption in the mid and high frequency range. This is a cushion, if you take a look at microstructure, it has lot of air pores in it. So typically the acoustic signal or the sound energy is getting converted into heat energy inside these pores, because of which you get very good absorption in the mid and high frequency ranges. As I said, mid and high frequency is good, but if you take a simple 50 mm or 25 mm thick cushion, its absorption or alpha value, absorption coefficient, is rather weak or low in low frequency. It is not very well performing in the low frequency. If at all you are left with only an option of cushion, you do not have any other option, you have to go for a foam. Then if you still want low frequency absorption, then you can increase the thickness or the spacing between the solid backing. Solid backing can be your wall, so probably you should go for a 50 mm or 100 mm space, air gap, then mount instead of a 25 or 50 mm foam, you go for a 100 or 150 mm foam with a air gap. Then it can be made to or stretched to improve the performance in the low frequency also. But if you are simply mounting it on the wall surface, a thin 50 mm cushion, standard panels, boards are available. If you are simply going to mount it, then you can only expect a very good performance in the high frequency. Low frequency you cannot expect much. There are different types, perforated, fissured boards, textured materials, different types of patterns, textures are available. They are also available in the form of acoustic boards, hangers, geoacoustic tiles, lot of panels, nice looking, architecturally good looking interior, suited to different themes of interiors, panels are available commercially today. Other variants include acoustic plasters, sprayed fibrous materials, blankets, foam boards, carpets, fabrics are available. So there are lot of varieties, and this is one of the most predominantly used acoustic absorber as far architectural applications are concerned. The second type is panel absorber. Imagine a thin plywood panel mounted on a frame, there is a air gap, you have the wall section here. This also absorbs at a specific particular frequency bandwidth. The absorption is restricted to one or two specific bandwidths, which depends on the thickness of the panel, the area of absorption, and the air gap which is available behind, that is the spacing. Depending on these three variables, the density of the panel as well, depending on these three crucial things, density, thickness as well as the mounting distance, the absorption specifically varies. I will show you specific examples of how the absorption is. It typically resonates at a particular frequency. I am going to show you some examples. The third type is called cavity resonators. These are typically box shaped absorbers. These are also called Helmholtz resonators. The working principle is they actually trap the acoustic signal. It can be specific boxes like this, or it can be panels with perforations, in which each of these perforation are going to act as an acoustic cavity, inside which the signals or the incoming signals can be trapped. This signal can be a simple void, or this can be lined for improved absorption, and these are typically well performing in the mid and low frequency range. Of course it depends on the width of the cavity, that is the diameter or the cross section of this whole thing as well. The resonant frequency, for example, at which frequency this cavity is going to be effective, or if you have a specific frequency in which you have to address, say for example your hall or your room is not performing well, or the reverberation time is excessively high at 125 hertz or 63 hertz. In this case you have a formula, you know the frequency now, velocity is fixed, now you can determine the dimension and the cross section of the cavity as well as the volume of the cavity, which will be able to arrest frequencies at 63 hertz, frequencies of 163 hertz or 125 hertz. There are different types, individual cavity resonators or perforated panel absorbers. Like I said, it can be perforated boards or it can be slit resonators. Some examples, you can have glass wool backing behind this, you can have foam backing behind this. There are different types and the performance varies. I will show you some examples. Apart from this, they can also be separately suspended in the form of specific boxes which act as resonating cavities, or like I said, it can be individual cavities which can arrest very low frequency sounds, typically used in recording studios where low frequency creates a lot of problem because of the smaller volume of the room as well as the type of sound signals which are generated. A few examples, first let us start with cavity, panel resonators, panel absorbers. Let us take an example, you have a wall, solid wall, you are mounting 25 mm thick glass wool, then you have a panel, plywood panel which is 8.4 kg per meter square. Typically what you get a sharp absorption around 100 hertz or close to 125 hertz, you have a sharp absorption of around 0.7 alpha or absorbing coefficient of 0.7 close to 125 hertz, but after that the performance is almost, all the alpha values are almost 0. You get very good absorption in this part, after that it is dropping down. But if you take a look at the NRC, it will show 0 because it is only taking into account frequencies after this particular frame. This lower frequency of 63 and 100 hertz is not covered here. If at all you are requiring this particular frequency absorption, sometimes thin panel absorbers would be really of good help. The absorption also varies with the thickness as well as the presence or absence or type of material used for the backing. Now I am increasing this glass wool from 25 mm to 50 mm. The material is same, wall everything is same, just the thickness has increased. Now you take a look at this, the absorption, sound absorption, the frequency has shifted further lower, now it is getting much closer to 63 hertz and the absorption coefficient is also increasing. You also get a very high absorption, it is shifting towards a low frequency. It is a good way of good strategy to use in case you are requiring very specific frequency in which there is a problem in the room or your hall. Now instead of a solid panel, if you have a slated panel, you have certain slots here, 25 mm thick glass wool backing, same wall material, plus you have a 6 mm thin panel and you have slats here. Look at the absorption coefficient, low frequency like you saw in the previous one, you do not get much in the low frequency range. A proper or an perceivable absorption coefficient you will get somewhere around 250 hertz where it is above 0.5, then you get a better absorption in the mid frequency, and in the high frequency range it is eventually dropping down. This is with a 25 mm backing. Now if I increase the backing from 25 to 50 mm, then you take a note, the absorption slightly gets a shift, you also get realizable values somewhere around 125 hertz, here itself it is crossing 0.5 absorption alpha value, and then you get a good absorption in the slightly low frequency range around 250 500 you get good absorption, after that 2000 hertz it is eventually dropping down. Just a variation in this thickness. Apart from this, the type of slats, the thickness of slats, is there a thin backing behind this, a cushion backing behind this, or what is the dimension? Instead of slats, if you have porous or perforations, the kind of absorption you are going to get is going to be different. Take a look at this now, instead of a slat you have a perforated facing. Now your NRC value is very good, the absorption coefficient pattern, you also get a good absorption in the mid and high frequency range. Here the critical thing is what is the diameter of this perforation and what is the distance between the perforation. So first I will be defining, here it is 3 mm dia and the spacing between center to center spacing is 9 mm, and what is the backing, here I have given 50 mm. Now the moment I am adjusting, decreasing it, increasing it, or I am varying this perforation type as well as the spacing and the diameter or dimensions of it, then the absorption coefficient or the performance of the material itself is going to vary. For example, in this case I have a open area of around close to 9%. I can increase this. If I increase this, the material is going to give better absorption in the low frequencies. So it is kind of variable. You have to actually get an understanding of how the material is going to behave with 3 different things, in this case spacing, diameter and the backing. Now so far we have been looking at acoustic absorption. So inside a hall you need a reverberation time, you need specific type of signal to noise ratio and acoustic absorption. For this you were using the factor called noise reduction coefficient and alpha or the absorption coefficient. Now let us talk about sound insulation. 2 things we are talking about. First was acoustic absorption inside a room. Now we are talking about sound, partitioning or insulating sound between one room to the other room, say a source room to the receiver room. It can be a noise source or it can be a sound source which you want to really arrest. For this, similar to NRC, we use a term called STC or sound transmission coefficient. Any particular material, say it can be a door, it can be a window or it can be a wall system, typically there is a standard which asks you to go for an STC rating of say 35, 40, 50. There will be specific STC ratings. Say for example you are designing a boardroom which is next to an open plan office. There will be a specific demand which says that the STC rating of the partition used between these two should be say 45, which means if there is, the boardroom requires around 30 or 35 dB as a background noise. Even if the source room, that is the next room, that is open office, if the sound signal goes to say around 80 dB, here you should be having around 30 dB, which means a 50 dB reduction will be required between these two. In that case, the sound insulation or the sound transmission class which we call is, should be carefully chosen such that it is higher. It is again a single number rating of a particular material or an assembly's ability to resist airborne sound transfer. Here we are talking about airborne sound transfer. There are different modes: airborne, structure borne sound. Now we are specifically focusing on airborne sound, that is air to air sound transmission at specific frequencies between 125 to 4000 hertz. There are different types of insulation, like rigid panels. You can have something called SPF or spray polyurethane foam. Then you have SIP, structural insulated panels. Different varieties, variants are available. Then you have blankets, bat insulation. Specific applications demand different type of sound insulating materials. We refer to a simple term called transmission loss. You have sound transmission by inserting, you have certain thing called insertion loss or a transmission loss. Without this particular material, there was this much amount of sound transmission happening between the source room and the receiver room. After I insert the particular material, there is some amount of transmission loss which is happening. This is determining the efficiency of a particular material. Similar to noise reduction coefficient, this is also determined at different frequencies and then totally you represent it in terms of something called sound transmission class. One important thing you have to notice, say for example there are 2 rooms separated by a partition. Simply the partition itself might have a very good sound transmission class. Say you have a gypsum board, 2 sets of gypsum board with some glass wool insulation material inside. It may have a very good sound insulation. Say there is source room and there is a receiver room. You have a gypsum partition plus you have a glass wool, then you have the second gypsum panel. This has a simple partition is available. Now source room to the receiver room, you may have this particular thing can have an STC of for example 45. A good STC value, sound transmission class is available. Moment you insert a particular window or a door, the STC of a door, this is STC of partition. Now you insert a door and a window. This is not openable, just a see-through window. For example, the door which you choose has an STC of 35, the window which you choose has an STC of 30. Then you have to tally or account for all the three things together, which is referred as composite sound transmission class. When you have 3, 4 or n number of different elements across the wall or a partition, then each of its sound transmission properties or sound insulating properties have to be accounted, which we commonly refer as sound transmission class or composite sound transmission class of a particular partition. Now this is a weaker link. If you have to really improve the sound transmission of the whole partition system, then you have to really address this particular window. Say instead of a single glass you go for a double glass unit, or you go for a laminated window panel which will be slightly more sound insulative. Then you address the door, you check whether it is a single door, double door, lead lined doors. Lead lined doors typically give you a better sound insulation in the low frequencies. You can go for acoustic gasketing, sound insulating gaskets, then you can improve the acoustic performance of the door. There is another component here. Say a particular supplier might give you a STC of the door as 35. This is something which you find in the materials catalog. This is a laboratory tested value. You also have something called field STC. This is a laboratory tested value. So you have to actually give certain concessions for its performance in the field. Moment you have certain installation related things, you cannot do such a fine installation like they do a testing in the laboratory. So accounting for all that, if you are doing a practical design, go for a slightly higher STC rating. Instead of 35, it is suggested or advisable to go for 38 or 40 STC, so that you can actually achieve an STC of 35. It is a general design consideration which any acoustic designer typically does. Simply putting it, a sound transmission class between say 40 to 50 is considered to be very good. Higher it is, say higher above 40, it is considered to be typically good between the rooms. That is, even if you have about say 80 dB sound on the other side, you are going to get 35 to 40 decibels if you have a STC in this range. Below this it is fair, and it is very poor if the STC ratings are 20 to 25. I am going to give you some specific examples of this as well. If you have a STC between 20 to 25, it also means that the speech between these two rooms, source room and the receiver room, is going to be audible with each other. Typically STC of the panel, say you have gypsum board, you have a plywood panel, there are different types, ranges or regions in which the sound reduction is more effective. There is a specific range called mass law region where the density of the material increases. So the higher density material and thickness you go for, the insulation properties increase. But there are two ends to it. In the lower end you have something called resonant region where the material start resonating to low frequencies. Typically it happens below 100 Hertz. Again it depends on the material and its dimensions. Typically in the lower side it happens. In the resonance region this is not proportional. Whatever thick, whatever density it is, when it resonates, the acoustic insulation is very poor. You cannot interpolate or extrapolate in this region. Again on the higher end you have something called coincidence region where different planes of acoustic signal coincide with each other, and again the insulation property drastically drops down. Getting certain specific examples, let us take a single layer of gypsum board, a thin gypsum panel, say around 13 mm or 15 mm gypsum panel. This is a absorption sound transmission class or the sound insulation property at different frequency, the red one, this is what you are going to get. Now if you add a cavity, add two specific gypsum boards, you are trying to increase this particular number. The STC value from 27 you are able to achieve 34. Now you have a glass wool associated with it, you can raise it to 40, you can increase the width of it from say 75 mm, you are getting it to 125 mm. Now from 40 you have a slight increase, you have a air gap, that is you have a air gap here, the same 50 mm insulation glass wool is put up here, you are getting a marginal increase in STC. You can take a note of the curve here. Now further to increase this is what we had in the previous graph, we had 41 STC. you can actually replace this wooden studs with specific metal studs with gasketing. You will have a very good increase in sound transmission class. In this example, instead of this particular wood, if I am going to introduce a metal stud with certain gasketing on both sides, I am kind of isolating both the things. I am actually arresting the sound transmission path, with which I am able to get from 41, I am trying to improve, I am able to improve it to 47 STC. Further to it, there are specific types of studs, metal studs, which are further good at isolating the sound transmission path, that is airborne sound transmission path, it would be able to arrest further. So we will be able to achieve, for example, with 2 lines of gypsum on both sides with a specific type of acoustical stud with the insulation of 50 mm and air gap on both sides, we can raise it to up to 59 STC, which is really a good STC to achieve between the rooms. So typically you have to understand, as the type of STC requirement increases, the amount of STC is essential, higher STCs are essential. There are various strategies like going in for thicker panels, adding another board, 2-3 boards, or introducing an air cavity, introducing insulation material, changing the stud types, or adding panels on both the sides, increasing the total air cavity. Depending on these things, you can actually attain an improvement in terms of STC. Common mistake which people do in the industry, when you have false ceiling, typically people stop this particular panel at the false ceiling level. Ideally, when you need a perfect insulation between both the rooms, it is suggested that you raise this partition up to the ceiling, clear ceiling height, do not stop it at the false ceiling level. These are certain common things, mistakes which are done. So you have certain thing called through the ceiling attenuation class, where through the ceiling, false ceiling, it gets in, passes through this and goes to the receiver room. So it is a good practice to get it further. Other common considerations are like, so you have 2 panels, there is one board here, there is one more board here, this is a source room, this is a receiver room. If you are placing say switch boxes on both these things, certain common things like do not place it side by side, it is a better advisable thing to place it in a staggered manner. Anything like staggering these, some principles, common principles, logical things can be applied so that an effective STC can be attained. How do you calculate the level difference between these rooms? This is a simple example. Say you have a room A, room B, source room and receiver room. Typical example in hotels or apartment buildings. Typically in hotels the problem is more because some of the rooms have connecting doors. Sometimes they make use of it as suites. They can open up these double doors, so they become suites together, this whole room is rented out. But when they close it, there is a typical problem of sound transmission from one room to the other room. So when you have to calculate this, for example, you have the transmission loss of this particular partition. Here you have different types of wall section, there is wardrobe here, there is a door, double door here, then there is a simple wall section, thin wall section, there is a thicker wall section here. Accounting for all this, you take the composite transmission loss, then you take into account the absorption which is present in the second room divided by the surface area of the partition. Together if you take, then we will be able to determine what is the level difference. Ideally what happens, you will not, in practice you will not be required to calculate the difference, but you will know what difference you need to achieve. You know that the source room is going to produce something like 90 dB, whereas here you want to ensure 35 dB. So you know what is the delta T required. The possible options are, you increase the transmission loss, you take a look at each of these elements and increase the transmission loss, or you increase the absorption in the receiver room, you make the receiver room more absorbing, then you will also find an associated improvement in terms of the overall sound transmission or the sound reduction which is attained. Closing this section, so far we looked at different indices of measurement. We looked at 2 key things. One is acoustic absorption, where we started with reverberation time and talked about noise reduction coefficient and specific absorption at different frequencies, how it is important. Other thing, we looked at the different type of materials, porous absorbers, panel absorbers and cavity resonators. And the second thing we looked at is sound insulating material, where we talked about transmission loss and sound transmission coefficient or STC. How do we calculate, and how do we calculate the transmission loss between two different rooms. We also looked at few examples of how do we increase the STC of a particular partition system. Thank you.